I do, I should share this. Right. Can you all see the slides? Yes, okay. So in this presentation, I'm gonna tell you about some aspect of the work package one, which is also divided into tasks. So we had a task related to bootstrapability, a task related to integrability. So this task is about ADS-CFT and strongly coupled quantum field theory in relation to the emergence of space-time, which is a topic that Joao touched upon on Monday. So in particular, today, I'm going to give you a proposal based on recent work, what can be done with work package one and how this fits within the collaboration. In particular, is going to be mostly Porto, Torino, and then APFL for the part of the machine learning. So the talk for today is called the Multiparticle correlators, coherent operator, and emergent on space-time. But I would also like to advertise the talk by tomorrow by Ignazio, which is the also the head of the particle physics group here in Madrid, about presenting the effective field theory group, which is actually the biggest group in Madrid, including several postdocs, senior people, and also students. So for the part that involves pretty much the work package one, maybe it's only me, maybe in the future some students. So let me start right away with some motivations about quantum gravity. And so as we know, GR is not UV complete, which in simple terms means that we don't understand the Hilbert space of quantum gravity. And this gives rise in various ways to some famous problems that have to do with black hole physics, unitarity in gravity, whether you lose informations during when you consider black holes in your scattering processes, and also implication for cosmology, what happened at the Big Bang, and so on. So what one would like to do in this regarding these questions, which are a little bit far away from being experimentally probed, is to have a first principle calculable framework where GR emerges from a macroscopic and quantum mechanical description. So having this framework, you can ask the question and then you get the answer, and this builds for you intuition of what should happen in the real world. Now, the ADS-CFT correspondence, also known as holography, is one such framework within string theory. So let me say something general about string theory, is that it's a mathematical framework for the 21st century, okay? But the crucial point is that in the ADS-CFT, you can formulate all the kind of puzzle that you find in flat space. And moreover, the crucial point is that from the ADS-CFT, you get an understanding of what's the flat space limit, and that gives you the idea that actually everything, the theory of gravity, the theory of quantum gravity in flat space is well-defined and consistent, despite the fact that when you try to get to it from effective field theory, you run into IR problems and UV problems as well. So therefore, for a theoretical physicist in the 21st century, answering quantum gravity puzzle in the CFT is realistic enough. So this is what this work package, that's the motivation for this work package. Let's see. Now, the dream in this holography would be the following. So the duality works in the sense that you have some CFT that you can think that lives at the boundary of ADS, which is some space with a boundary. And you would like to reconstruct any kind of gravitational physics just from a knowledge of the CFT. So in particular, in an example, this means that in the CFT, you compute some correlator, you transform this correlator into, and this correlator is dual in the theory of gravity to some amplitude. For example, you can think of a correlator in the CFT that computes the 4-point scattering amplitude of gravitons, okay? And then in this setup, what happens is that the quantum gravity expansion in G Newton, which is the effective field theory expansion we should be familiar with, is formulated as at large n. So the CFT has a central charge, say n, and n is large, and a strong tooth coupling. Okay. So the canonical, so the task here is to understand from the correlator, compute correlators, then transform them into amplitudes, and from the amplitudes reconstruct what happens to the particle in the bulk in the gravity side when they scatter. Now, the canonical example of ADS-CFT is string theory in ADS5 times S5, and this is dual to n equal 4 super Young Mills in 4 dimension. So this is, and then there are many cousins of this. So I will have in mind especially this example when I usually talk, but then in the end I will comment on generalization to other examples. And why also I like this example, because I would like to emphasize the importance of n equal 4 in other contexts, for example, the amplitude bootstrap context, where in particular many techniques that were developed for n equal 4 then turned out to be applicable more generally to other theories, and in particular also to QCD. So this is why this theory lies at the intersection of many developments that are related, can be related both to gravity and to amplitude in a fruitful way. So continuing with the dream that I was mentioning about, what happens that you would like to reconstruct the gravitational dynamics in ADS just from computing correlators. So a piece of the dream is the following. So if you start from tree level, let's say a tree level computation, which is done in the usual way by having a Lagrangian to start with and then computing diagrams, that's doable both in the gravity side, and it's also doable in the CFT side. And here it's very famous that there have been a magic match between these two techniques, between these 2 points of view on the same quantity. And I would like to remark that in the CFT, what you can do that will be the basis on, let's say, the developments in this work package is to use some more refined technique that come from the amplitude bootstrap, in addition to some first principle consideration on the spectrum, similarly to what kind of Andrea was telling you about before. So just a glimpsey sketch of the method, which will take too much to explain, but I think the philosophy is very clear and applicable in general. So it starts with some ansatz, which requires you to have a knowledge of the space of function that you want to describe the amplitude. And this means that you have a knowledge of the analytic properties of the amplitude, the discontinuities, the crossing properties. And you get this knowledge, for example, by studying a class of diagrams on their own, without referring to any particular combination that appears in the final theory. And then you try to fix these ansatz from CFT, which means you impose consistency with the operator product expansion that was mentioned in the previous talks. And here is where it comes to the first principle considerations about the spectrum. And not only that, you will also need some piece of technology of the CFT that has to do with the block decomposition and the inversion formulas, some rules, etc. So there are these two pieces of technology that you need to use. But the point of this CFT method is that it's successful. So in the case in which you have both an ADS computation and a CFT computation, which is the case for tree-level physics, this match is quite promising. And in fact, there is work from the past and also from the present that showed the beauty of this stage at tree level. Now, at one loop, I would like to emphasize that the ADS side is not doable. So you cannot go and write the Lagrangian, or at least if you try, it's going to occupy so many pages that is very useless. So it's unfeasible to do the one loop computation in the ADS, but in the CFT is doable. And so in this context, maybe sometimes we don't emphasize too much, but let's say the one loop and higher loop bootstrap program in ADS is at the frontier of this holographic dream, because it allows you to get information about the gravity side that is not available from any kind of ADS computation that you can do with standard techniques. Okay, And this is the work that I've been doing in the past years with James and Paul, which maybe are online. And if you wish me, I can give you more reference later offline. But I would like to pose a question that sometimes the bulk reconstruction problem is not well defined. So we should always think that we need to ask a question both on the CFT side and on the gravity side. So the question should make sense in both situations. And sometimes this lands you on a not well-defined problem. So a better case study for this program in the work package 1 is to have a situation in which both the CFT and the ADS side, the prescription how to relate the two is clear. So this is the proposal that I have for this work package 1, which is based on some recent work that I would like to mention. And this is the way it connects mostly with the techniques that comes from the amplitude that can be used also in work package 2, for example, or in other situations. So one would like to focus on some correlator, which is heavy, light, okay? And to have a concrete example of a heavy operator, here it is exponential of some parameter eta that multiplies O2, which you can think of the lightest operator of your theory. Now, this is a heavy operator, so eta is going to be a large number, if you wish. And so it means that in the path integral generates a back reaction to the vacuum, and therefore it generates, in this context, a geometry. And you want to probe this geometry or this heavy vacuum with a light operator, denoted here by OL. So this exponential of eta O2, okay, is a coherent operator. So here schematically, you can think of it as a summing over as the exponential series, where at each order you have some multiparticle type of operator, O2 to the n, okay? And now the point I want to make is that there are situations in which this eta here that is measuring the strength of the back reaction on the vacuum can be taken to range in a region where eta is both small and large. And this regime is well controlled on both limits, okay? For technical reasons, this is why it's BPS, okay? But probably being careful, this is applicable to other situations as well. And the point is that when this eta parameter is small, so while when the eta parameter is large, that's dual to a geometry, which is concretely calculable. When the eta is small, you can think of it, you can think of the heavy light correlator as an expansion in multi-particle correlators, where certain diagrams enter. Okay, and here are the diagrams that a schematic. Well, these are the diagrams that you can think that enter in the computation. Of course, when eta is 0, it's just you exchange the identity, so it's just the two-point function. Then you have some tree-like correlator when eta is at the first order in eta. Then you have some other tree-like correlator when at the second order. But one has to be careful with this idea of being tree-like, because actually the O2 square L here are at the same point. So as you can see from the diagram, this becomes a one-loop contribution. And if you keep going, this becomes a two-loop contribution. Okay, so the expansion in multi-particle correlator is capturing some diagrams, some loopy diagrams of the expansion of the heavy light correlator in eta is capturing some loopy contribution to multi-particle correlators. And so the idea here is that the heavy light correlator can be computed from other means through some wave equation, okay? And for the purpose of the investigation in the gravity side is a geometric detector. So the fact that you're able to compute it tells you a posteriori that there is a geometry where you can think that the light operator is propagating, and also gives you access to an expansion in multi-particle correlators, where the expansion you can think that at each time you insert a quanta of the O2 operator, okay? And So the idea is that the the heavy light correlator is resumming a particular sequences of connected loop amplitude, and this connected loop amplitude at the same time enters some multi-particle correlators that you can study on their own. Okay. So let me give you a little bit more detail on this because I think it's important. So if you study the correlator, the multi-particle correlator on their own, then you will start with the usual diagrams. For example, the one which is light, it has the disconnected pieces, the three-level pieces, the one-loop pieces, two-loop pieces, and so on and so forth. The one which has multi-particle level 2, let's say, again, has disconnected pieces, three-level pieces, one-loop pieces. Now, in the three-level pieces, it's again disconnected, because it's just the product of the one that you had before. So the disconnected for the light and the two-point function. And the new graph that enters in the geometry is actually a particular one in the diagrammatic expansion. And it's a particular one that, but to get the full one-loop contribution, you need to get the one from the geometry and another one which came from the disconnected diagram. So, and you can keep going like this, also considering multi-particle level 3 and so on and so forth. So the panels highlighted correspond to, in the gravity side, to a geometric expansion. And so one point that I want us to make here, respect to what I was saying at the beginning about the program of exploring loop correction in EDS, is that resumming the certain, let's say, ladder type of diagrams in on the loop expansion of the multi-particle correlator is giving you a geometric description in terms of heavy light correlator, but the full quantum gravity expansion of the correlator includes more stuff. So, for example, you have, if you can see my cursor, you have this diagram here, which is not captured by the by the heavy light correlator. Similarly, you don't have this, and you can keep going, and you don't have some other diagrams that appears in the actual loop expansion. So there is something particularly nice about some family of diagrams that get resummed and give you a geometric picture of a geometry, versus some other diagrams that are probing more refined information about the scattering in quantum gravity at different orders in G Newton. Okay, so with this, let me just give you some results that will be appearing, that just to motivate that this proposal here is rich. Okay, so you get a lot more information, and it's also calculable. Okay, so the gravity background are explicit in EDS phi times S phi, they're explicit, so you can plan like algorithmically to try to solve this heavy light correlator perturbatively from the gravity side, and it's a computation of wave functions. Already it's clear that there is a pattern, okay, and this pattern is kind of simple because it just captures some diagrams in the full loop expansion, and these are the diagrams that gives you a geometry after all. And the diagrams that are related to the example, that the simplest example that you can think of, when you have the light operator that is building your coherent operator as exponential of the light operator, are just ladder diagrams and derivative of that. You can do Regge physics, which means that in the background you can compute a null geodesics, and you can study its iconal phase. And that is actually something that a posteriori you can compute out of the correlator by doing the analytic continuation. You get a new CFT data. So, for example, triple particle data from gravity, which was understood to be there from the bootstrap, but I think here you can actually see it from an honest gravity computation. And the analysis of the full correlator is very rich, so reveals new non-trivial checks of EDS CFT, which is, as I was saying before in this context, getting more loops is getting you at the frontier of what you can explore about the gravity side. So it's one step towards better understanding of what happens with gravitational scattering in ADS. Then there is this nice feature that the correlators that adapt to get the geometrical picture are some sort of gravitational ladders. So they are simpler than the generic diagrams that has been seen to appear when you study loop corrections of individual light correlators. And the relation that this proposal in the work package can have with other people is essentially itemized here. So multi-particle correlators, you can get them by doing OP limits from 5-point function. That is what Vasco told us at the very beginning in the first presentation. 5 points and higher point functions are the kind of at 3 level are the ones that are being studied in Porto. It would be interesting to understand how to do integrability with multi-particle correlators in an equal 4. This has overlap with Torino. And then that would be very nice to systematize the way you do holography and you compute these wave functions from the gravitational perspective. And this might be something new to explore with machine learning codes, because it's true that you study some differential equation, but the way you translate the differential equation then into gravity information is not the standard one. So you know that there is a dictionary, normalizable mode, non-normalizable mode. So you need to do further things with the wave function, not just compute its moment. And then this physical picture of going from heavy light correlators, which change the vacuum and gives you a description of the vacuum as a geometry, is applicable more generally. So in other background, ADS3 times S3 and other M-theory backgrounds. So this picture works, okay? And the type of diagrams that enter this computation in this particular work package are the same type of diagrams that are familiar with in amplitudes. So that's and similarly, the techniques that you use here, these techniques that you use are the same ones that you get studying amplitudes in the in QCD, for example. So I think this is a fruitful work package that, together with the other task, might lead to nice projects within our consortium. So let me thank you for the attention. Hopefully I am on time. Yes, good. And if there are any questions, I will be happy to answer.
Can I ask a question?
Yeah, sure.
So the ladder diagrams in flat space are usually associated to some large impact parameter physics. Is that correct? So is this the same in ADS? And related to this, are the CFT data that you get out sensitive to this, like large spin? Can you say a little bit more about the physics?
Yes. So where is this? So here the question about the ladder diagrams, you're thinking about the case in which you do gravitational scattering flat space, right?
Yeah, or more generally, but yes, case in which you're dominated by small deviation and like small angle. Yeah.
No, okay. Here, no. These are just the physics here happens in a different way. So you don't get them just in a limit of a small parameter. In fact, perhaps this picture is I think it's intuitive, but also maybe a bit misleading in the details. You don't just get ladders, you also get derivative of ladders. So your full function has more feature than this. And that's why you don't get it just in a limit, but you get the full picture. And they are... So if you compare with with individual multi-particle correlator, you get in this case, you get other diagrams. For example, here in the light case, you get also some zigzag diagrams that do not show up in these gravitational ladder diagrams. So they don't show up because they are related to the physics, the why they don't show up, or at least in the first few examples, is that in the CFT, they're related to propagation of CFT data that appeared in the previous correlator. So here it appears in the in a way that is disconnected. Now, it's true that in the CFT, it's a little bit ambiguous to define some kind of connected CFT three-point functions versus the full connected CFT three-point function. But this is what is suggesting the computation, so that there is a piece of the CFT data that you can call like connected. And the full CFT data is that plus another piece. That other piece might be, it came from other correlator a previous order, and therefore gets more correct. It gets more complicated. So there is a physics at each order that is has to do with some connected diagrams that is simpler versus a more complicated physics that has to do with other refined information about the CFT. So, for example, coming back to the question about the data, here you find triple trace data in both diagrams, but in one case, the dependence on spin is simpler. So in the case of this diagram is simpler, and in this case is more complicated. To be more precise, here you start finding polygamma in spin, and here you get still rational function in spin. So they're both contribution from triple traces, but somehow the way they are arranged in the gravity side seems to be different, or but maybe different is not the right word, but seems to be more, seems to have a nicer physical effect. That is the fact that these diagrams in the end construct a geometry. The others are there, but they have a different purpose. So it would be interesting to understand, like, maybe I can define I can define some three-point function in some limit, or some kind of subtracted three-point functions that gives you the idea of connected three-point function that only enters in this diagram and do not enter here. But I'm not at this stage of understanding.
Thank you.
Thanks for the question. So maybe to get on time, maybe I can pass the mic to Ife.